Our next speaker will be Michael Karisk, and he will give a talk about on how to design a Linux kernel interface. Please give him applause.
Good afternoon. You can hear me okay, can't you? Sounds like you can. Alrighty. So I'm going to talk about Linux kernel interface design. I suppose I should begin by saying that this is mostly not going to be a technical talk. I'm mostly going to talk about process. So if you want to leave, now's your chance. So I see this sort of problem mostly from a process and perhaps also a social perspective. I want to talk about some examples of the kinds of things that go wrong and why I think it's mainly a matter of process. If you got here early, you saw a rotating slide deck that I had up, which had a design problem that we've lived with from BSD for more than 30 years now. It's a consequence of the kinds of problems I see happening again and again in Linux kernel development, but we're not the first to make these sort of problems. We're perhaps just, again, the best at doing these things, even the best problems. And the point about these problems is when we make these mistakes, we live with them for a very long time. Okay, so just a little bit about myself. I'm the maintainer of the Linux Man Pages project. I've been involved with that project for about 15 years now. I write a lot of what some of you folks probably read from time to time. I spend a lot of time looking at APIs. I have done a lot of API design review testing over the years. I wrote a book about APIs for Linux as well. So a lot of looking at APIs for quite a long time and seeing some things that happen again and again. As I said already, this is mainly a process talk, not a technical talk. And there's briefly the sort of things I want to talk about. So a lot of it is kind of obvious, and it's a question of why we don't do it or why we haven't done it much in the past. So when it comes to APIs, implementation of an API is the least of the problems, I think. You know, if you get the performance wrong, you can fix it later. If there are bugs, well, they can be fixed. They're a bit irritating, but they can be fixed. The very big problem, of course, is actually getting a proper design for the API. API designs are hard to get right. They are usually, you can't fix them once you've released them. The reason, of course, is that if you fix them, that usually means breaking the API, and of course, you stop this guy smiling. It's one of the push-button ways of getting Linus to yell. Is to say, well, we just need to fix the API. Maybe a few applications will break. That will be pretty much guaranteed to get Linus unhappy. But the other thing, of course, is if you get this wrong, thousands of user space programmers are going to live with your mistake for decades. And the BSD sockets example I had at the beginning here is just such a case. So when it comes to APIs, there's a lot of different kinds of APIs in the Linux kernel. Pseudo file systems, netlink, virtual devices, signals, system calls, multiplexer system calls, things like IOCTL and PRCTL, and these ways of sneaking things in so they're not a new system call, but really they are. We'll just call it an IOCTL. And get less review and maybe less resistance. Mainly I'm going to talk about system calls for my examples at least. So one of the first things I want to say about designing APIs is when you're a designer, you really need to start thinking a lot more outside your use case. So one of my favorite examples here is POSIX message queues. I don't know if you're familiar with POSIX message queues. Basically, it's a message passing IPC mechanism in the kernel. You can queue up messages, and the messages have priorities. Higher priority messages get delivered sooner than lower priority messages. The usual use case of POSIX message queues is you've got a reader sitting around in the queue, always reading incoming messages, dealing with them pretty quickly, and perhaps now and then a writer comes along and puts a message in the queue, but because there's always a reader around, there's never many messages in the queue. Perhaps at the most a few messages in the queue, a lot of the time 0 or just 1 message in the queue. The people who originally wrote POSIX message queues coded for the expected use case. POSIX message queues were added in Linux 2.6.6. Several kernel releases later, there was a Red Hat engineer. I was actually giving an iteration of this talk, and I was talking about this case exactly, and he was in the audience. And that's how we met. Anyway, in Linux 3.5, there was an engineer from Red Hat who was making some changes to the POSIX message queue APIs. Not so much the APIs, but things like changing the limits on the APIs, default values for the APIs, setting up a few new /proc interfaces to control the behavior of the APIs. One of the things that he wanted to do was raise the limit on the number of messages that you place in the queue from 32K to 64K. Now, those are funny numbers when you think about the use case I just talked about. Most of the time, there's very few messages in the queue. He wanted to raise the limit to 64K. In other words, the customer he was working with wanted to put vast numbers of messages into a queue, treat the message queue as a kind of dump. And he was investigating the kernel code that dealt with message queues. Remember, message queues have priorities. That implies messages have to be sorted. And he realized that the sorting algorithm inside the kernel amounted to a bubble sort. So he knew that pretty soon after he made these changes for his customer, he was going to get a bug report about how terribly POSIX message queues performed. The thing is, of course, for the usual use case, bubble sort is fine. And that's what the original developers coded for. Okay, the Red Hat developer concerned fixed this problem. Better sorting algorithm. So I think the first takeaway from this story is, when you're designing an API, people in user space are endlessly inventive. They'll find any manner of different ways of using your API. And they massively outnumber you. Every crazy thing that is possible to do with an API, they will find a way of doing it. There will be someone who does it. And even that wasn't such a crazy use case. It's just an unexpected use case. So that's one moral of the story. But you might say, well, is this such a big deal? There was a performance problem. It got fixed. We're good now, aren't we? That kernel developer also turned around and broke the API in 2 different places. Now, they were kind of minor breakages, so no one noticed for a while, but they were nevertheless breakages. One was that there was actually, I'll rephrase that. This was not such a minor breakage. This caused some people real pain. One of the changes actually placed a hard limit on the number of message queues you could create on the system of 1K. That limit didn't exist before. And with the changes, not even super user could override the limit. And so for third-party developers who are creating applications based on message queues, they were having to say to their customers, yes, you can use our product now, but if you want this number of message queues, you're going to have to rebuild your kernel, which is not a very acceptable solution when you're selling a product to your customer. Several kernel releases later, that finally got fixed. And then there was this was a more minor problem, but one of the things you get, there's a pseudo file system you can use with message queues that allows you to see the number of data bytes in a message queue. And before these changes, this correctly reported the number of user space data bytes that were in the queue. After these changes, it included some kernel overhead. Who knows how the kernel overhead was calculated? The point was that from the point of view of user space, it made this field of no use at all. Again, finally, that was fixed quite recently, but many kernel releases later. The problem, of course, is there were no unit tests. And it's pretty much guaranteed that if you don't have unit tests, then eventually someone is going to screw up your API. Make some refactorings that'll change the behavior in subtle ways that may not get discovered for quite a while. So the obvious stuff, unit tests are about preventing behavior regressions, and even just making sure that as you go out the door, the API works as you advertise it's supposed to work. And regressions in the Linux kernel, in terms of kernel user space APIs, have actually been surprisingly common. And just a couple of examples then. So in Linux 2.6.12, or up until that time, there had been an F control operation called fsetOwn. This was a way where you could say, I want to monitor a socket, or it was part of a process of saying, I want to monitor a socket or perhaps some other kind of file descriptor, so that when an input becomes possible in the socket, for example, I get a signal to say input is possible. Until Linux 2.6.12, with this operation you could say, I want the signal to be targeted to a specific thread in my process. In Linux 2.6.12, things got changed so that that signal was no longer thread directed, it was directed to a process. That meant that the signal could be delivered to any thread in the process. Now, no one noticed that for quite a while, and when someone did eventually squawk about it and say, this actually broke my application, this was already several kernel releases later, like 20. And then we've got 20 kernel releases with the new behavior. Do we revert to the old behavior? Well, maybe there are new applications that depend on the new behavior that are going to get broken by the change. So then we had to invent another F control operation that gave us the old behavior. Probably many of you have heard of the iNotify API. It's a technique for monitoring file systems to see whether files are changed or created or removed or renamed, monitoring changes in the contents of a file system. I have to just catch up with myself now. Oh yes, okay. So there's a flag that you can use with the iNotify API called IN1shot. It's used when you want to say that when you want to get just one notification from a file system object. Once you've got that one notification, you don't need more notifications about that object. This is useful for some use cases. What iNotify also has is something called an INIgnored event. INIgnored is a way sometimes file system objects that you're monitoring disappear on you. Perhaps the file system was unmounted for some reason, for example. When that sort of thing happens, iNotify gives you an INIgnored event saying, I'm going to cease monitoring this object now. By design, you didn't get that event for a one-shot notification because, hey, you asked for a one-shot notification. You knew after that it was going to be ignored. So we have these two features, and then several kernel releases later, when the FA-Notify work was going on. FA-Notify is another kind of file system monitoring API. When this work was being done, there was a lot of refactoring of the common code between FA-Notify and iNotify, and silently things were changed so that now IN1shot did generate an INIgnored event. Just another little example of regressions that happen because there are no unit tests. So we get regressions, but also we get things that are going out the door and they don't even do what it says on the box, what it says on the tin. You know, something's supposed to do something. Does it actually work? Well, IN1shot again, one-shot notification, iNotify was released in 2.6.13. Give me one notification on a file system object and then disable monitoring. It actually didn't work. If you just tried it, it had no effect. If you tried using IN1shot to monitor a file system object, you'd actually get continuous events whenever that object was changed. In other words, there was zero testing before it was released. And eventually that was fixed after I noted that, and it was eventually fixed in 2.6.16. I don't mean to give iNotify a hard time, by the way. It's a useful tool, but it's such a rich API that it presented a lot of examples for me, and I also spent a lot of time looking at it at one point. So iNotify suffers for the fact that it got my close attention for a while. But so let's stick it to iNotify just a bit more. iNotify has a concept called event coalescing. The point is you might be monitoring a file system, and the file system has a lot of activity going on. You're monitoring perhaps the contents of a directory, and perhaps there's a file in that directory that is being updated. There is a process that is continually writing to a file in that directory. Potentially, iNotify can deliver you one notification for every write to a file in that directory. This may be more than what you want. And one of the features that iNotify has is something called coalescing of events, where if the new event that has appeared is the same as the next preceding event, then those two are coalesced into one event. So if you get a sequence of events that are all the same, rather than queuing hundreds of events to you, if the application program hasn't processed those events yet, then they're coalesced into a single event, so you don't get this vast long queue of events. That came out in 2.6.13. By the Linux 2.6.24, someone noticed that actually the coalescing of events was not with, well, when you got a new event, it was not coalesced with the event at the back of the queue, but with the event at the front of the queue. In other words, the newest event was coalesced with the oldest event on the queue, which makes no sense. So there was very little testing that went on there. Perhaps it was like, I put an event on the queue, I put another event on the queue, they're the same, they coalesced. More examples. Receive mMessage. Receive mMessage. This is a relatively recent system call in Linux. It's a performance optimization. It allows you to, in a single system call, read multiple datagrams from a socket. A lot of these more recent system calls, of course, they're all about I/O optimization. Receive mMessage is just another example. Now, a lot of system calls like this that block benefit from having a timeout argument. And the person who invented or implemented receive mMessage got a review comment to say, hey, it would be nice if we had a timeout argument on this system call. I suppose that the idea of the timeout was it'll be a timeout on receiving all of the datagrams. So you might have done a receive mMessage call where you say, I want to get 5 datagrams, and you give a timeout of, let's say, 3 seconds. And if those 5 datagrams arrive in the 3 seconds, you get 5 datagrams. But if less arrive, you get fewer datagrams because the timeout expired. The way it actually works is the timeout only gets started after each datagram arrives. So in other words, if you make the call and no datagrams arrive, you never time out. So again, there's clearly no serious testing of the implementation. So all of these kinds of problems also could have been avoided, I would say, with unit tests. I'm going to take that as obvious. You could, it seems to me pretty obvious. So, whenever you're adding a new kernel API or you're refactoring an existing API, write some unit tests. One of the problems with that historically was there was not a good home for unit tests. There's been a long-established project for the Linux kernel called the Linux Test Project, which does some good work, but the problem with the Linux Test Project was historically the tests lived out of the kernel tree, and they typically got added to the tests typically got added to that project sometime after kernel APIs were released. So LTP could sometimes be used for finding regressions, but it was seldom good for finding bugs in kernel APIs before they were released. Things have got a little bit better in recent times because starting in 2014, there's now something called K-self-test, which is in kernel unit tests, and some people actually write some. There is even a mailing list and a wiki page. Most importantly, there is actually a warm body, so a paid human being that looks after this, which makes a huge difference. Of course, if you're going to write unit tests, you will want to have a specification, don't you? For me, Andrew Morton is the most quotable kernel developer. I love this quote. Programming is the act not just of telling the computer what to do, but telling other programmers what you want the computer to do. Both are important, and the latter deserves care. To which I would add, which it often does not get. So let's poke receive end message a little bit more. The timeout bug, the problem there, of course, was no one wrote a specification. What I mean is something like this. Now, I'm not going to talk about the details here. This is my fantasy of what the person who suggested the timeout argument was wanting. Now, no one ever elaborated what it should do in any detail. So when it came to implementing it, the kernel developer, who didn't really understand, it seems, the timeout framework within the kernel, ended up doing something quite useless. But there needed to be some sort of specification like this, and that simply was never created. And of course, when you've got a specification, then you've got a target for implementers to work towards. And if you don't have that specification, well, how can you tell the difference between the intention of the implementer and what they actually did? That difference, of course, is what we call a bug. And we can write unit tests, and we can even help people review our APIs. So where do you put your specification? Well, a good place to start with is the kernel commit message. A lot of kernel commits for new APIs or API changes, there is no real explanation of the change, not even in the kernel commit message. But some kernel developers do actually manage to write a good specification in their commit message. Of course, the best place to put these specifications is in something like a man page. So one of my arguments, and I'm biased, is that if you write a good man page, it gives you a good specification for testing. My bias, though, has some basis in experience. So I've gone through this process of writing man pages for kernel APIs where there was no man page, and then used those man pages as test specifications for the APIs. And so for these two system calls here, uTimeIn-SAT and TimeRefD, which is actually a family of system calls, I wrote or co-wrote some of the man pages and then turned around and wrote tests based on the specifications that actually I created, unfortunately. But by that means, I found a bunch of bugs in both APIs. One of the problems in general in terms of API design is what I call the problem of the feedback loop. And then the problem goes like this. You're a kernel developer, you put a new API into the kernel, it's going to be available to user space. That will land in a kernel stable release some weeks later. And perhaps several months after that, it'll land in a distribution release. And it's only then that people will really start using that API. So in the worst case, your bugs and your design failures are only going to be found perhaps 6 months after you did the work of the original implementation. And by then it's probably too late to fix anything because you've now got a solidly fixed API, and if there are design faults in it, it's probably not possible to fix that API without breaking at least some applications that already use that API. Or to put things another way, what you really want to get is as much feedback as you possibly can before an API is released. And then, how do you do that? Well, you want to publicize things as widely and early as possible, And so these are some of the things I think that kernel developers need to do. And things have got a little bit better in this dimension, but there's still a lot of work to do yet. So you want a detailed specification somewhere. Perhaps it's a man page, perhaps it's some other documentation somewhere. Some programs that actually demonstrate how the API works. This lets reviewers actually see how the API is supposed to work, try and run those test programs, expand them, and so on. You want to email as many lists and especially as many relevant people as you possibly can. Nowadays, there's also a dedicated mail list for people like me and one or two other people in this room, I think like Dimitri, who are interested in knowing about kernel API changes to user space. There's several groups of people who care about API changes. Obviously, I care. Things like the C library projects care, S-Trace project cares, and obviously users care as well. Another good way of publicizing an API, and some kernel developers have actually done this sort of thing, is to write an article for LWN, because that's a very good way of propagating information about your API to a wide audience. Unfortunately, that last piece is really the exception rather than the rule. Of course, you'd only do this if you really wanted to get a lot of feedback on your API, wouldn't you? Perhaps you really just want to get your API into the kernel as fast as possible to solve your problem. I'm sometimes cynical that this is a strategy. Let's get the API in there with as little noise as possible to solve my problem. And I won't explain too much about how it works because then people won't point out the faults in the API. If you're a subsystem maintainer, I would watch out for people who do that sort of thing. So another thing I think is really important in terms of API design is writing a real application. And here I'm going to stick it to iNotify again. Say it's just because I paid a lot of attention to iNotify and it's a rich source of examples. I think iNotify is a good thing. It just could have been a better thing. Okay, so the whole idea of iNotify, again, it's about monitoring a file system to find out about changes to files, renames, reads, writes, deletions of files, and so on. Before we had iNotify, we had an earlier system called dNotify, which did some of the same thing, but in a much poorer way. And it was a framework that was based on delivering notifications using Unix signals, which was pretty uncomfortable. And before even that, what you were reduced to doing was actually polling the file system using system calls like readdir and stat, which is incredibly CPU intensive and just generally resource intensive. So iNotify did make things better, but I kind of contend that it could have made things better still. And I'll just show some examples. And the backstory here for me was, from my book, I wrote a chapter on iNotify, and I thought, I understand this API and what it does. And then sometime later, I actually tried to write, I'll call it a real application. It wasn't a real application. It wasn't anything that I ever released that people could do the things useful with. But it tried to emulate what a real application might try and do in terms of monitoring a file system. And what the application did, the intention was to monitor a directory subtree and keep cached in my application a model of the directory subtree under a certain point in the file system. So I would record in my application all the directories that were, and subdirectories and subdirectories and so on, that were maintained under this subtree. And the idea, of course, was that whatever the state of the file system was, my application should always perfectly mirror that state so that I'm realistically monitoring the state of the file system. That took me 1,500 lines of C code, and I wasn't even producing anything useful. And okay, that includes some comments there, but let's say 1,000 lines of C code. And I wrote it up on LWN, so you can go and read the long version of this story. And then I understood, that iNotify is a good thing, but it leaves you with still a lot of problems to solve. And some of those problems, I think, could have been solved by iNotify. So a couple of things that were tricky about iNotify. One thing is when you get notifications from iNotify, you get a host of information about the changes to the file. One thing you don't get, or perhaps two things you don't get, are the UID and the GID of the UID and the PID of the process that made the change in the file system. And sometimes that might be really useful to know who made this change, because sometimes it might even be you, because you're monitoring a file system subtree in your application, and your application also does some work inside that file system. Well, your application will end up generating notifications. And sometimes you want to know whether those were notifications that you generated or that some other application generated. But there's no way of doing that with iNotify. So some people would say, you know, if I give the UID and the PID as part of the notification, that's an information leak. Well, then maybe we restrict this just to privileged processes. Another aspect of iNotify, and I don't want to necessarily call this a fault actually, because I think it's an inevitable limitation of the API. Monitoring of a file system directory is not recursive. If you monitor a directory, you'll find out about events on that directory and also the immediate descendants of that directory, but you won't find out about events on subdirectories of that directory and the subdirectories and so on and so on. What you've got to do in that case is for the subtree, for every directory and subdirectory in the subtree, you've got to add another iNotify watch. This is it's a big subtree, directory subtree. This is a relatively time-consuming operation. So one of the aspects of iNotify that is nice is it provides a way of getting you good information about file rename events. What I mean by this is you might be monitoring a directory subtree, and within that subtree, a file gets renamed from one of the subdirectories under the tree to another directory under the subtree. And assuming you're monitoring all the subdirectories, then you'll get a notification, two notifications, a move from notification saying the file left this directory and it landed in this directory, a move from and a moved to event. But there's a couple of details that make this feature more painful to use than it should be. The moved to and the moved from event are not guaranteed to be consecutive. On a multi-processor system, you could get, it's rare, but it can happen, that you can get another event from some other file system event in between those two. I've never seen more than one, but I've sometimes seen at least one. And the other thing is that, well, if you're doing a rename event from one directory to another directory within the set of directories you're monitoring, you'll get the two events, move from and a move to. But maybe you're moving the file to somewhere else outside of your monitored tree. In that case, you'll only get the move from event, but there won't be a moved to event. And you don't know in advance. So what you've got to try and do is match these two events up to see, well, I got a move from event. Did it move to another directory? Was there a move to another directory that I'm monitoring? And of course, the two events are not contiguous. They may not even arrive in the same read buffer. You might have to do another read from the iNotify file descriptor to get the event, which may not even be there. So you've got to do reads with timeouts. It's inevitably racy, and so it's inevitably racy, which means sometimes you fail to match the events. And when you fail to match the events, what in effect that means is you're going to treat, potentially, if we're talking about a directory rename, the directory as though it was being deleted, and then when it appears somewhere else, because it was actually really a rename, that directory will be recreated. And perhaps if you're doing recursive monitoring, you'd have to recreate all of the watches for all the subdirectories that you wanted to monitor. This is expensive. Things would have been so much simpler if the kernel could have just guaranteed those two events are going to be contiguous. So this is what I mean. You can only get a feel for what the real design problems and requirements are from an API by writing non-trivial applications that really test the API. And of course, this should really happen before it's released to the wider world. It's no good finding these problems later. And if you can't fix the problems, at least document them so that other people can point at you and poke fun at you and reject your API. Okay, so how am I going for time? I've got 10 minutes. Is that true if I've got 10 minutes? Something like that. Just a few technical things that maybe I'll just rush through. I just said I wasn't going to talk much about technicalities. There's a few technical best practices, though, now that have become established. One is that system calls should allow for extensibility. This usually means having either a flags bit mask argument where you can set bits in the future to say, hey, now the system call does something new. And you might say this seems fairly obvious, but, well, it wasn't obvious in the past because we've had repeatedly this kind of pattern where we had the system call without the argument, and then, without the flags argument, and then we had to invent another one with the flags argument. You probably have heard historically of the dupe and the dupe2 system calls in the kernel. Well, of course, now that we have a dupe3, and so on and so on. And so this is just a few of the examples. Again, I wrote an article about this on LWN. There's an alternative possibility where you've got a structure which is an argument, and that structure has some sort of size field associated with it. And by changing the size of that size field in new iterations of the structure, then you signify some sort of behavior change in your API. There's nowadays, thanks to David Drysdale, who's actually floating around this conference, a nice article that talks about a lot of this, or a nice text file in the kernel tree that talks a lot about these points. Of course, if you have this flags argument, then you want to make sure that all the unused bits are zeros, because if you don't check that there's 0 bits there, then if some crazy user puts random bits in those arguments, then later on when you try and make a use of those arguments in a future version of the kernel, suddenly those old applications do strange new things. And Linus doesn't say, oh, that application's broken. He yells at you for trying to change the API and breaking applications. And there have been real cases of this where some features that have been added to the kernel or attempted to be added have had to either be abandoned or changed because some system calls didn't check their flags arguments. It turns out if you go and look at the kernel source that a vast number of the historical system calls don't check their flags arguments. The most famous one is the open system call. The flags argument there, if you specify random bits and the unused bits, the open system call just ignores them. We had a chance to fix this in Linux 2.6.16 with openat, but no, we just maintained the consistent open behavior instead of checking the flags. I was sleeping that day. Okay. There are some other consistent patterns as well nowadays. If you create a system call that creates file descriptors, you should always have a close on exec flag, a way of creating the file descriptor so that the close on exec flag is immediately turned on. This is close on exec, if you're not sure what it means, by the way. When you create a file descriptor and then you do an exec, then file descriptors by default are preserved for the new program. This is a feature. But sometimes you don't want that to happen, so you turn on the close on exec flag so that when you exec a new program that you don't quite trust, the file's automatically closed. But there are certain kinds of race conditions where in a multi-threaded program, a process, one thread opens a file and then tries to set the close on exec flag, and in the window in between, another thread does a fork in exec, and the new program gets the file descriptor. The close on exec flag, or a lot of the system calls nowadays that create file descriptors, at the time you create the file descriptor, there's a flag, something like oclo exec, that says, when I create the file descriptor, set the close on exec flag immediately. If we want to turn this around to the other way, we would have said, I think, that this was actually this is of course not a Linux problem. This is a problem, a design failure in the original Unix. Close on exec should have been the default behavior. Anyway, new system calls should always do this if they create file descriptors, to have this option. Some system calls have timeouts. Some blocking system calls have timeouts. Common cases, they have relative timeout options, but with relative timeouts, if you're catching signals and so on and the system call gets interrupted and restarted, timeouts can creep. There should always be an option for an absolute timeout as well. PRCTL, F-control, IOCTL, these multiplexed system calls. What I really want to say about these is, don't do it. I know there are valid reasons, like if it's a device and it's a single use case, it kind of makes sense. But some people try and sneak monstrously large APIs in as IOCTLs. One of the problems with using these multiplex system calls is that if you decide to extend your new feature later on, you might end up multiplexing your multiplexed system call. So, for instance, seccomp was which there's been a few people talking about seccomp at this conference. Seccomp is a feature for limiting system calls an application is allowed to make. It started out, you enable it using a /proc API, and that's the ancient history, but then it was extended by using, I'll rephrase that. Then the API for enabling seccomp was moved to PRCTL. And then at a certain point they realized, well, we actually want to have different options for enabling seccomp. And should we add another option to PRCTL to get this different behavior? And then you have to think, well, if we do that once, are we going to do it twice or 3 times or 4 times? Or maybe we really need another system call. Reason prevailed this time. And so we actually got another system call. Capabilities. Capabilities are one of my favorite amusing stories. Probably many of you are familiar with capabilities. The idea of divide the power of root into small pieces. The idea then is that instead of having set user ID programs on your system where you've got an application that's got the power to do everything on the system if it gets compromised by an attacker, that if the program just has a few capabilities and it gets compromised, then it's much harder for the attacker to make the program do dangerous things. So divide the power of root into small pieces. And then you're a kernel developer. I'm adding a dangerous feature to the kernel, a dangerous user space feature. What capability do I assign to my new feature? And you've got 2 choices. Either you add a new capability just for your feature to the kernel, which you don't usually want to do because we don't want an enormous number of capabilities. Or, thank you, we find one of the existing silos, one of the existing capabilities, and that sort of best fits our use case. And we put our new feature into that silo. And hopefully each of the different silos is small enough that we divide the power of root into small pieces. Now there are about 1,500 places from memory in the kernel where there are checks. Does the user process have this capability? Then it's allowed to do this dangerous operation. But about 1/3 of those are capsysadmin. In other words, if someone's got capsysadmin, the game's over. It's just as good as being root because there's so many pathways for things you can do with capsysadmin. I call capsysadmin the new root. Again, I wrote about that was the title of the article. There is a pathway out of this problem, but no one. It's a lot of work. Okay, I won't say anything about this, but if you're dealing with 64-bit arguments and structure fields, you want to take care about this. Just to point you to a couple of places to read more about that. Testing. I can't say enough about test. My motto, and this is based on a lot of experience, you show me a new API, I'll show you a bug. It's actually really surprisingly easy to find bugs in new kernel APIs after they've been released. And you might think, well, bugs are fixable. Yeah, but bug fixes are ABI changes, and applications end up needing this special case. You know, which kernel version am I on? Is it the one with that bug, or is it a new good kernel? Okay, so some people do the right job. I'm just going to call out one person who did a magnificent job a few kernel releases ago, a guy called Jeff Layton, who added a feature called open file description locks. They fixed a serious problem with traditional POSIX record locks. I won't go into the details, but he just did everything nearly perfectly. He wrote a patch where he clearly explained the rationale of what he was doing at great length. Some example programs. He wrote messages into the mailing list. He wrote an article on LWN. He wrote a man pages batch. He engaged even with the glibc developers. And if kernel developers are overloaded, glibc developers, it's even worse. They are incredibly unresponsive, not because they don't want to be, it's just that there's way more work than there are people. So if you ever want to get involved in a project that's really important, they really need more people. So he had to resubmit that patch many, many times. And he did that. And he eventually got it in. And he made it all look really simple. If you want to get involved in kernel development, I would say the stuff I've talked about here is one easy path to get involved in kernel development. There's, in terms of reviewing and testing and documenting APIs, there's a lot of ways to get involved with the kernel. There's a lot of low-hanging fruit, a lot of design errors that are easily found, a lot of bugs that are easily found, and actually often easily fixed. And just to take, or to say some things about that, so things that you can do, make kernel developers explain what they're doing. Kernel developers, it turns out, are often pretty bad at explaining. And if you just make them explain in more length, you find out interesting things about their APIs, and often ways to suggest things to be improved. Documenting APIs is a good way of finding bugs, because you can't write good documentation without understanding the API, and you can't understand the API without testing. A classic recent example of this for me was a guy called Heinrich Schuchart, who wrote the FA Notify man page about 20 kernel releases after FA Notify was released. But he found 6 significant bugs while he did that. And he wrote patches to fix them all. It was really great work. So, it's a very good way of getting involved in kernel development. Thank you very much for your time. I'm sorry we've run so close to the time, but is there time for 1 or 2 questions if there are any? Yeah? So what's one question this year?
So I'm a subsystem maintainer for I2C, which is more on the device driver side. And I wrote an in-kernel API like 4 releases ago.
Yeah.
And I think I knew the relevant people, but it was really hard to find relevant people who had time to review. So I'm all for your do the specification things. How optimistic are you that we as a community have the bandwidth to review all these specifications if they were created? I think there's a scaling problem in there.
Sure, but I would argue that reviewing specifications is I would argue that reviewing specifications is easier than reviewing code. So there's no perfect solution to this, but I would say this at least makes your job a little easier, but doesn't solve the problem of insufficient reviewer bandwidth, of course.
Ladies and gentlemen, may I ask you to remain seated? It is very difficult to hear the questions and the answers. So please remain seated until the talk is properly finished. Thank you very much. Are there any other questions?
Okay, thank you.
Okay, thank you very much.